Okay, section 10.5, picking up where we left off on problem 29. We're writing a two-column proof. Given that quadrilateral ABCD is circumscribed about circle P, we want to prove or show that AB plus CD is equal to AD plus BC. And we're on the fifth step here. So we're substituting. AB plus CD is equal to AH plus HB. So I'm just taking what AB is equal to plus, and I'm taking what CD is equal to. So I'm substituting H plus HB in place of AB and CF plus FD in place of CD. Likewise with DA plus BC. So I'm adding those two together, therefore I'm adding these two sides together. On 6, I'm substituting again because I want to somehow equate these two things. That's what I'm trying to prove. So let's see if we can change this up so that it's equal. What I can take is, let's see, I can take HB and CF, and if I go back to statement 3, I can put what is equal to them, or congruent to them, and for them. So I'm substituting again. So I'm taking HB and putting BG in its place. I'm taking CF. CF is congruent to GC, so I'm putting GC in its place. And this statement becomes this. For the second statement, notice that I left AH and FD alone. So I'm going to leave the same thing alone here. So I'm going to leave, HB and CF. HB and CF went out in this one. So I was looking at the wrong statement. I'm sorry. So DA plus BC. How can we change it? We can take out, since we got a BG and a GC in this statement, I'm going to leave BG and GC alone. And I'm going to take these two out and put something in their place. So for DE, I can put FD. For EA, I can put AH. Because that's what it tells me up here, that they're congruent. Now I'm going to use the commutative property of addition, which just means it doesn't matter what order you add in. I'm going to get these in the same order as what I have here. So I'm just going to reorder so that it's FD, then AH, then BG, then GC. So I have the exact same thing here as I have here. So in my final step, I can substitute one more time. So DA plus BC and AB plus CD are both equal to the same thing. So I'm substituting DA plus BC in for all of this garbage. And I get what I wanted to prove. Speaking of garbage, we have space trash on this next problem. Orbital debris refers to materials from space missions that still orbit Earth. In 2007, a 1,400-pound ammonia tank was discarded from a space mission. Suppose the tank has an altitude of 435 miles. What is the distance from the tank to the farthest point on Earth's surface from which the tank is visible? Assume that the radius of Earth is 4,000 miles, round to the nearest mile, and include a diagram of this situation with your answer. So I've made my diagram here. Here is the tank, 435 miles altitude, so that's above the surface of Earth. Earth has a radius of 4,000 miles, either going this way or this way, to a point of tangency. So when it's talking about what is the distance from the tank to the furthest point on Earth's surface from which the tank is visible, that would be at a point of tangency, because after that point, now we're going to be on this other side. Imagine this is the sun, and light would be hitting here, and then past this point we would be in shadow. So this would be the furthest point on our surface from which the tank is visible. So we're going to use Pythagorean theorem. My hypotenuse would be 4,435, and a squared and b squared. So to solve for d, and I'm letting d stand for distance, d squared is equal to, so I'd want to subtract 4,000 squared from both sides. And then to get d, I need to take the square root of both sides. So d is equal to the square root of the quantity 4,435 squared minus 4,000 squared. And that is approximately, to the nearest mile, 1,916 miles. Okay, for 33, write an indirect proof to show that if a line is perpendicular to the radius of a circle at its endpoint, then the line is tangent, and that should be to, not of, to the circle. Part 2 of Theorem 1010. We are given that L is perpendicular to ST, and ST is a radius of circle S, and we want to prove that L is tangent to circle S, that it only touches the circle at exactly one point, because that's what a tangent line is. So it's saying do an indirect proof, or sometimes called proof by contradiction. So a proof by contradiction is when you assume the opposite of what you're trying to prove, and then somewhere in the process of proving, you get a contradiction. And if you have a contradiction, then that means that the opposite, basically what you are trying to prove, is true. It's kind of confusing, but you'll get the idea here. So what we're going to assume is the opposite of what we're trying to prove. Assume L is not tangent to circle S. Okay? So assume that L, and we're going to use this diagram to show that. So L is not tangent. So that means that it's going to intersect it in more than one point. This is what we would call a secant line. Since L intersects circle S at T, it must intersect the circle in another place because it's not tangent. So if it's not tangent, it has to intersect somewhere other than T. We're going to call this point Q. Then ST has to be equal to SQ because S is the center, so the distance to the edge here is the same as the distance to the edge there because that's the radius. And triangle STQ is isosceles. So we have an isosceles triangle. Two sides are congruent. Therefore, my base angles must be congruent. T is congruent to Q. But in our given, we said that L is perpendicular to ST. So if it's perpendicular, L is perpendicular to ST, then that means it's a right angle there. And if we're saying that our base angles are congruent, then both angles T and Q are right angles. But this, and here's our contradiction, this contradicts that a triangle can only have one right angle. So there's no way for a triangle to have two right angles in it because 90 plus 90 is 180. Then you'd have nothing left over for the third angle because the three angles must add up to 180. Therefore, L is tangent to circle S. So since we came to this contradiction Once again, then that means that what we are trying to prove is true, since we assumed the opposite is true. Number 35, PQ is tangent to circles R and S. Find PQ. Explain your reasoning. So I went ahead and drew in a few things on this diagram in order to figure this out, because just with the information that they gave us there, we can't get a clear picture of what's happening. So what we want to find is the length of PQ. PQS, and then I'm just going to call this point Q. So, whoops, can't call it Q, sorry. Let's just call that T. So PQST would be a rectangle if I draw this segment in. So if I draw this segment in here, we would have right angles, of course, here and here, because that is tangent to the two circles, and I would have a length of 4. My opposite side also needs to be 4. Since this radius is 6, subtract 4 from 6 and we get 2 for this length right here. And I want to solve for this length because opposite sides of a rectangle are congruent. So if I can find A, then I'll have my answer for PQ. So we have a right triangle, which I split off over here, TRS. I know that this length is 2. I know that my hypotenuse is 10 because I'm adding the two radii together, 6 and 4. So using Pythagorean theorem, and subtracting 4 from both sides, and taking the square root of both sides, we get that A is approximately 9.8. So if A is approximately 9.8, then the side opposite from that, PQ, is also 9.8, because PQ ST is a rectangle, once again, and we use Pythagorean theorem. So this is my explanation. We use Pythagorean theorem to solve for A. And that's section 10.5. Take care.